Our next presenter, Jon Kerchief, I actually was thinking the other day that I've had him every year he's been here at USI, and so it's been a pleasure for me to introduce a project that he worked on this summer. He started this summer at his internship at AK Steel and continued on through the rest of the semester. So I'll let Jon introduce the rest.
Thank you for the introduction. As he said, my name is Jon Kerchief, and I designed the software platform for a hot aluminum prediction model for AK Steel. First, I'll begin my presentation by going over a brief background of the project, and then I will go into the detail of the design. AK Steel Rockport Works is located just north of Rockport, Indiana. In Rockport, Indiana, just north of the Ohio River. It has many facilities used in the creation of manufacturing of flat rolled steel coils. I had the pleasure of interning in the continuous galvanizing line this past summer. AK Steel creates two different products. On the left, you can see is galvanized steel coil. It is shiny and metallic color. It's used in stainless steel, such as kitchen appliances. On the right is galvanneal steel, which is a dull gray color, and it's used in the automotive industry. The CGL, or the continuous galv line, it has two coating pods where the galvanization occurs. These coating pods contain a mixture of zinc and aluminum that is molten and circulating throughout the pod. There are two, like I said, there are two different pods. The first pod is a pre-melt pod. It's smaller than two pods. This is where the zinc ingots are dropped into to prepare the zinc solution before it enters into the main pod. And then there is also the main pod, which is larger than the two pods. The steel strip is actually passed through this pod, and this is where the galvanization is occurring. This is an example of the main pod used at AK Steel. As you can see, by the red line, that is the steel strip going down into the pot, around the sink roll, and out of the pot. This is where the zinc material is actually occurring, and the galvanization occurs, like I said. An ingot mixture is very important to the process of galvanization. It controls the aluminum concentration within the pot. On the left, you can see a jumbo ingot, and there are three different types of AK Steel, each weighing 2,400 pounds. And each different ingot contains a different aluminum concentration, which affects the pot differently. Also on the right is a pallet of Breitner bars. Breitner bars are 20 pounds, and they contain a higher concentration of aluminum, which will bump up the aluminum concentration more quickly. AK Steel wanted me to focus my project on bake hard coil schedules. Bake hard is bake hardenable steel, galvannealed steel, and it's used in the production of car parts such as car doors and other car manufacturing parts. With the fact that it's used in car parts, it needs a stricter quality and coating process to actually create a quality part. In order to create the part, the bake hard steel strip the pot has to be within 0.131% and 0.134% aluminum concentration. If it goes outside that concentration, dross will occur. Dross causes imperfections on the strip. It is basically a tiny little black speck, and whenever the door is stamped, a pimple will occur and it will cause a defect in the car door. There are two different types of dross. There's top dross and bottom dross. Top dross, as its name, it floats on the top of the pot, and it's a frothy metallic material, byproduct that is created when the steel strip passes through the zinc pot and forms a compound of iron, zinc, and aluminum. Bottom dross floats to the bottom of the pot, and it's a sand-like material, also created by the same effect of the steel strip passing through the pot. As the steel strip is going through the pot, dross is continually circulating throughout the pot, and you can kind of picture it as snow globe. shake a snow globe and snow circulates around the snow globe. If there's too much pot or dross in the pot, this may affect quality of the steel strip itself. If there's too much dross on the strip, the coil may need to be worked or even be rejected. Rework coils can be manufactured, cut off the imperfections, and still be sent to the customer, whereas rejected coils must be melted down and started from the very beginning of the process. And a rejected coil costs 3 times as much as a reworked coil itself. AK Steel wanted to improve its quality process and reduce the amount of rejected and reworked coils. During the summer, AK Steel approached me while I was interning in the CGL to help design the software for this prediction model for my senior project. And they wanted the program to be able to predict future aluminum values within its 2 pots, and be able to. They had an existing Excel file which they wanted to use as a template. The existing Excel file, most of its functionality was not working, and it was several years old, started from an engineer several years ago. They wanted to reformat the program and then change its design so that only focusing towards their bay card coil schedules. They wanted the program to be completely automated by VBA. VBA is Visual Basic for applications, and it's used in many different Microsoft Office programs. And they wanted the program to predict up to 12 hours in advance of the aluminum concentration inside the pot with a 2% accuracy. The user interface must be user-friendly, and it needs to generate reports and charts to quantify the results. Also, the program contains proprietary information, so security measures need to be taken to keep this information secret. I broke my project down into several different categories: data acquisition, user interface, the program's functionality, reports and charts, security, and the testing of the program itself. This is a flowchart of my project. First, the user will go to the coil schedule page, and they will import a coil schedule. Then they will go to the user input page, and they will enter all known conditions about the pot, and such as the aluminum concentration, line speed, and pot temperature. They will also enter an ingot mix, which they decide for bay card coil schedules is typically a 1 black to 1 white jumbo ingot mixture. Once they enter all this, they'll hit a button to run the program, and reports and charts will be generated. If the results are not within the specs of what they want, of the 0.131 to 0.134 range, they can go back through and try a different ingot mixture until they find results that work. First part of my project is the data acquisition portion. Coil schedule is released 1 to 2 days in advance before the product is actually run through the produced through the galvanizing line. The coil schedule contains many different parameters used for each coil and is used in the calculations of the aluminum concentration itself. The user will hit the refresh button in the top left, which will prompt the user to enter a password to gain access to an Oracle database where the coil schedule is located, and they will then enter a date, which the coil schedule is entered into the database, which will return the coil schedule. Next portion of the project is the user interface. User interface had to be easy to use, like I mentioned earlier, so I made a pop-up menu so that the user can actually enter all of the information inside one thing, and it will generate it into a table. Also, the pop-up menu the user can actually enter 3 separate ingot mixtures, which the program will be able to evaluate all 3 at the same time. Also, buttons, as shown, were created to help the user step through the process itself and automate the program. This is an example of a pop-up menu. As you can see, the user will enter the start time of the coil schedule, along with the initial aluminum concentrations for the pre-melt pot and main pot. The line speed and pot temperature are usually maintained at the same level, so they're kept constant. The user will enter the ingot mixture, how many blacks, whites, and orange colored ingots they want to use. If they can then run the program. If it's not working, they can say change ingot mixture, which will prompt the user to a second page where they can enter a second or third ingot mixture. The program, once everything is entered, it will run through all the calculations and predict the start of each coil along with the aluminum concentration, and also predicts the time and color of each ingot dropped into the pre-melt pot. There are alarms that generate, shown here. These are predictive alarms, and they will tell the user what coil and when the coil will actually trend outside the wanted and acceptable range. This is an example of a danger one alarm, which will actually tell the user when it actually goes outside the 0.131 and 0.134 range. As for reports, I created two different reports: a summary report, which is a one-page document summarizing all the results of the program itself, and a detailed report, which tells the aluminum concentration for each coil and is color coordinated to show which range. If it falls outside the acceptable range, or if it's within the range, it's green, yellow, and red. Also, there are the charts. The program generates charts, 3 different charts. There's a pre-melt pot chart, one showing only the pre-melt pot. The main pot chart, which shows only the main pot, and a chart that shows both the pre-melt and the main pot together. This is an example of the chart that shows both the pre-melt pot and the main pot chart. The pre-melt pot is shown in blue and is slightly higher aluminum concentration, and the main pot chart is shown in green below and is maintained at a more constant level. This is the main pot chart. Is basically a zoomed in replication of the zinc, the detailed report for the main pot chart, and it shows the limits and the acceptable ranges in red and yellow, and you can actually visibly see where it starts outside the acceptable region and trends into the acceptable region. And it only plots the predicted coil schedule time that will actually start, and it tells you what time you started the coil schedule and what time it will actually end in the title. Over time, the process may change. So I needed to create a way to test the accuracy of my program. So I created an accuracy report, which is automated. The user can actually bring in the measured values taken by the materials lab at the AK Steel, and it will compare the calculated predicted results of the program with the measured results taken by the materials lab, and calculate the percent error between predicted and measured. I used the coil schedule shown earlier and went through and entered in all the initial conditions into the main pop-up menu that I showed you earlier in my presentation, and executed my program. The program predicted the aluminum concentration at 0.57% accuracy, which is well within the 2% constraint given to me by AK Steel, and has very good results of my program working. As I mentioned, the program contains proprietary information. Only certain authorized users, such as the shift managers and process engineers, will be using the program itself. So in order to keep the proprietary information kept secret, there have been passwords for each sheet that only the shift manager and process engineers will know the actual password to enter and actually use the program itself. Also, another way to keep the proprietary information hidden is to only show the sheets that contain information that is critical for the user to see. And the bottom picture shows the menu that helps let you be able to see every sheet, and you can pick which sheets you actually want to see. Hopefully, in the future, my program will be implemented into the actual process of the Descartes schedules. It can be used as a monitoring system during the process of actually producing the pull schedule, Descartes pull schedules, and be able to monitor and see if the program or the aluminum concentration will remain acceptable throughout the pull schedule itself while it is running, and be able to make adjustments if it will not. But the main goal of my project is to be able to use the program well in advance of the pull schedule actually running through, being processed throughout the CGL. In order to do this, they'll be able to find an ingot mixture that works perfectly for the specific pull schedule. In summary, I was able to develop a software program in Excel that models the coating zinc concept, the continuous galvanizing line of AK steel. It predicts well within the 2% accuracy and generates reports and charts that summarize the results. It contains an easy-to-use interface with alarms, predictable alarms, and it also is automated and tests the accuracy of the program itself. I have also made security measures and created a security system so that only authorized users may use the program itself. I would like to thank my supervisor, Steve Boston, and mentor, Andy Hearn, who helped me throughout the summer working on this project and this semester as well. Whenever I had a question, I would always shoot them, and I would always be able to talk to these two men and be able to have an answer. I also like to thank my advisor, Dr. Deersing, who helped me along the way of the semester of finishing my project. Donna Moore, without her, nothing would get done. And my family and friends for being able to be here and support me. And without them, nothing would actually ever get done. Any questions?
I just have a little question on your testing
Yes.
of your program. How many, did you just do that once, or how many times did you test, or you tested for different types of schedules?
I only tested it for one pull schedule. The Descartes pull schedules are only processed maybe once a month at the AK Steel. And this is the